All right, guys. So today's video, we are going to talk about batteries. Okay. Now, after rereading the standards and stuff for the AP test and all that jazz, today's video is just going to be talking about and explaining the process of how a battery works. Okay. Um, then we'll be going into some of the stuff talking about Gibbs free energy, cell potentials, stuff like that. Okay, but today's video just about batteries, how they work. Okay, so batteries are redox reactions. Okay, and redox reactions are reduction, which means gaining electrons, and oxidation, which means losing. That looks like a G. Losing, there we go, electrons. Okay, so a standard sort of, they're called voltaic cells or galvanic cells. A standard galvanic cell looks like this. We've got container number one. It's got a little bridge, a little membrane, and then number two. Okay. Now, with this, they are filled with liquids. We got a purple one and a red one, let's say. Okay. One of them is the anode, and the other is the cathode. And this we are talking about little strips of metal that are put in to these containers so that these half reactions, is what they're called, can work. All right. So we've got the anode, we've got the cathode. Now what happens at the anode is always oxidation. What happens at the cathode is the other one. Think, Joe, think. Reduction. There we go. Goodness gracious. You'd think after however many butt ton years of chemistry I've had, I'd be able to think of reduction. Okay. Now, the anode could be metal, let's say X. The cathode is metal Y. Okay. In the solution, we have a salt of metal X, and the salt of metal Y is in this one. Okay. Now, these galvanic cells or voltaic cells move forward spontaneously through half reactions. Okay, these half reactions are the reduction and the oxidation reactions of metal X and metal Y. Okay, so the half a reaction for the anode, since it is oxidation, is going to be the metal going to lose a certain number of electrons and its charge of plus N. So we'll put N here and its charge of then plus N. So that would be the oxidation. We'll put this in purple. Oxidation half reaction. Okay. Now we've got the reduction half reaction. And that would be yn plus a certain number of electrons gives y. Okay, so the flip reactions, the ends might not necessarily be the same for both of these metals, but that's a topic for another time. However, those are the reactions that are happening in this voltaic cell. Okay, so we've got the anode, which is here. We've got the cathode, which is here. And we have here, which is called the salt bridge. Okay. Now, the salt bridge is what is going to keep this thing moving. This reaction without the salt bridge might happen like quickly for a second, and then it'll stop. But this is what'll let it happen continuously for a longer time period. Okay. So let's look at these half reactions real quickly. The half reaction for the anode. So let's do a little zoom in to the half reaction. I drew this wrong. Happening at the anode. Okay, this is oxidation, and so it's going to start out fine as a full piece of metal. Okay, as this process goes on, it is going to lose more and more atoms of metal to the salt solution. Okay, it is going to lose more and more ions, and so as time progresses, it is going to look deteriorated. Okay, and so that's what's going to be happening at the anode. At the cathode, we will have, as time goes on, it looks standard right now. As time goes on, it is going to be adding atoms from the salt solution. And so it is going to be adding metal particles, okay? Since reduction is happening and we're forming metal ions, or not metal ions, metal atoms, they're going to be attracted to the actual solid here and forming more metallic atoms, and so the size of this node is going to grow. Okay, the salt bridge is to make sure that the I guess the charges of each of these solutions are staying the same. So as let's draw some more pictures here. Salt bridge, membrane. Okay, and the left one was purple. The right one was red. Okay, so as this reaction goes, then there's going to be a lack. Sorry, not a lack. There's going to be excess X plus N over on the left side, because it is a oxidation reaction. It is producing more charged X. And as the reaction goes on the right, there's going to be a lack of Y plus N. And so, to make sure that there's not an excess of these A- particles, okay, that form the salts here, the X plus is going to, excess X plus is going to transfer over across the membrane. It is going to require some osmosis pressure, but that's the whole reason the membrane is there. And so it's going to cross that membrane, make sure that these are taken care of, and that the reaction can continue. Okay, it will continue until either the anodes run out or the salt, the Y plus N and the salts run out of the solution on the right side. Okay, and this produces, as you can see, a certain number of electrons. Okay, those electrons will go from the anode. We'll put them in blue. The electrons will go from the anode to the cathode, and since the cathode has electrons, it will attract these Y and pluses, and that's what makes the growth of the cathode. Okay? So that is overall how a battery works. This is a galvanic cell or a voltaic cell. I'll write that out. Galvanic / voltaic cell. Okay, the important things to remember is that this reaction is reduction and oxidation through half reactions. Okay, these half reactions force the anodes and cathodes, anode, cathode, to undergo these processes, and the salt bridge enables the X plus to go over and form bonds with these A minuses. Okay. All right. Or is it the other way around? I think it might be the A minus goes over. Let me check. Okay, I checked it, and they both happen. So the whole point of the salt bridge is just to make sure that, like I said, there is a charge balance. Okay, so you don't want an excess amount of charge on the plus charge on the left, or an excess amount of negative charge on the right. And so as the electrons move over, you want to make sure that there is a balanced amount of charge going both ways. Okay, sorry, I just wanted to make sure I'm giving you guys the correct information. A lot of this stuff I do research, but that part did not come up while I was looking at stuff. So I wanted to make sure I was telling you guys the right stuff. All right, so that is a galvanic cell. Now, an electrolytic cell, I'll write that out, electrolytic cell. Okay, an electrolytic cell is the opposite of galvanic. Okay, so since a galvanic cell or a voltaic cell happens spontaneously and goes one direction, the electrolytic cell would be the opposite of a galvanic cell in the fact that the reaction, that same reaction that we saw up top, is going to go the opposite direction, and so X is going to be reduced and Y oxidized, and that requires, since the forward reaction was spontaneous, this reverse one requires the input of electricity. Okay, so while a galvanic cell produces electricity, a electrolytic cell requires electricity for the reaction to take place. And so a combination of electrolytic and galvanic cells could make a rechargeable battery. Okay, you put charge into your battery, and it reverses this process. And allows you to use that battery again as it was meant to be used. Okay, so that is all for today. We will talk about next week half reactions and their cell potential, and so their potential to produce electricity, their potential to work together, and how that relates to their Gibbs free energy. And then we will be done. That is it for the rest, for all of AP Chemistry. Okay. Good luck studying for the test if you're taking it. If you have any questions, make sure you're emailing me, and I will see you guys in the next video. Have a good weekend.